Okay, so there were two main conditions to write the amplitudes, okay, and let me recall. One is very simple, is the fact that dimensions of the amplitude with three legs, 3-point amplitude has dimension of energy, and for PT is dimensionless. These would be important conditions. And the second was this condition related with the little group that I can, even if you didn't get it, at least you know this condition should be fulfilled. And now you can start, and it's a very powerful one, okay? So you can start building this amplitude just by knowing these conditions, okay? So for the particle one, every time we should fulfill this condition. The amplitude when you evaluate by this weight, when you put this weight for each spinor should be equal to e to the I theta, the helicity of the particle one, okay, to fulfill this property. Of course, these spinors will be contracted, as we have seen, okay? Okay, so this is an important condition, okay? This is what almost give, well, 80% and 10% come from dimensional analysis, okay? And similarly, of course, for the other states. Okay? And following this, that's it, okay? You sit down and in a few minutes you can see how it goes. Okay, let me recall something about the 3PT that yesterday, because it was a little bit chaotic. I have it in the notes, it's there, but I forgot to say. I think I say it in words, but I didn't write it. It's probably good to clarify. When you look at the 3PT, I was already saying that because you can see that P1 is equal to P2 plus P3, and when now you square this thing, you have P1 squared, okay, P2 plus P3 squared, and now because are massless particles, tell me not to write up there, so Pi square is 0. When I square this thing, I have a 0 here, equal to square of the first one is 0, only the cross term remains, P2 times P3, okay? Sorry, this I don't put the mu's, these are with the, okay, contractions, squaring of the, with the normal Lorentz index mu, okay? So you see this is 0, and it's 0 for all of them. All Pi times Pj are 0, okay? These are contraction with mu, okay? Let me put it here explicitly. They are not invariant, Lorentz invariant here, so this is why for massless particles, this does not give you any process, okay? Realistic process. Okay, this condition tells you that all should be 0, and the question how to avoid this thing is to go to complex momenta, or if you recall now the condition we had Pi times Pj as a function of the spinor was this Ij, Ji. Okay, so if it's not complex, we don't have to demand anymore that this is the complex conjugate of this thing. Okay, so Ij is not anymore the complex conjugate of Ij. They are decoupled, you decouple them. So since you are extending a little bit, you are saying that when we are saying the momentum P alpha theta, that you wrote it as a spinors. I don't know if it's to hide this. So since we are decoupling these things, transforming in the different SL2C. Okay, there is like a enhancing the symmetry to LC2C cross SL2C. Okay, but don't get lost about this. Okay, the question we are going to assume that you realize this condition, and now it could be this 0 by keeping either this 0 or either this 0. Okay, this is the point. P times Pj can be 0 in this method because either or either the bracket, the angle brackets or the square brackets are 0. There are two possibilities, and it can be shown is in the notes, but the lack of time is telling me not to do it, that when you choose, for example, the 1, 2 to be 0, you have to choose also the, okay, you can choose one, no? Okay, let's say P1, P2. Okay, say you can take the square or the angle to be 0. Okay, if you choose this one for the 1, 2, also the others like 2, 3, also the other squares, and 1, 3 are 0, okay? So conclusion is that either all ij are 0, or second possibility, all. You cannot take 1, 2, P1, P2, this, and for the other, the other. In principle, it looks like so, but not when you look at the details. And this is in the notes, okay? So either you go for killing all the, putting to 0 all the angle bracket or the square brackets, okay? And we went through a possibility already the other day, and we got, I think I explained everything now, okay? And we went to the possibility as we were discussing, leading order. In the expansion ij over lambda, or ij over lambda. And then leading order, we already discussed this type of guy. We have a scalar. Okay, every time I write a discontinuous line will be a scalar. Okay, I can put it one time. And this straight line, as usual, fermions. When I put minus, helicity minus. If it's a fermion, it's minus a half. Okay, the helicity. And a scalar has no helicity. Okay, and we already said that this has to be proportional. The proportionality, we call it Yukawa coupling times. Now we have to put the numbers here to select the particles because we do it like this. Okay, now the brackets will be the spinors of the particle 2 and 3. Okay, has dimension 1, fulfill rule 1, and if I transform I put in my amplitude e to the theta here, okay, okay, because these are spinors, it will transform like a fermion, that is a spinor also. Okay, so if you transform are different things, okay, but for the fermions, now, of course, the spinor, both are spinors, okay, so spinor variable, kinetic variable, let me call it, transform like spinor field, okay, so that's the easy way, okay, and of course, you can have it also for the plus plus, okay. It will take you little to realize that this is proportional to 2, 3 now square. Okay, because I'm changing the helicities and changing here the square half opposite. I miss here an I. Let me put it, I see now. Okay, this is plus here. And now you can ask yourself the other one. There is an extra one here that is plus and minus. Okay. 1, 1, 2, 3, scalar and 2 fermions. You see now it's relatively easy if you spend some time to build up what we want to build. The amplitude, the standard model of amplitudes. Okay, it's relatively easy with these two rules. Okay, you have to sit slowly seeing that everything matches. Okay, that's what I recommend you to do, and you get hooked to it, and you see, oh, okay, I can derive these things, and we will understand certain things in an easy way. Okay. That probably with the Feynman rules is more complicated. Okay, I told you, we cross the mountain, okay, now we have this rule, and now this is easy, okay? Even I don't know, I always say, even your grandmother can do it. You tell them, follow the rules and write me these things, please, for me, and they will do it, because it's a kind of like a Sudoku, it's an entertaining thing to put the factors 2, 3 here, okay? And this is, you could see that the only thing to have the right helicities should be, looks like proportional to something keeps the 3, the 2 here, okay, and the 3 down, okay, because the 3 is a plus, so I have to put it down. Minus 1 will transform as a e to the I to the theta 2, like a spin a half down, okay. We'll have this, but now I have to cross, I have to make it invariant to contract with something else. Okay, what could be the something else? Okay, it should be something else that should be the same here, some I, that I don't know who is, you have to derive it. Okay, but it should be the same in order not to change this property. Okay, if you don't put the same, now you will, when you do look at this property, you will change the chiralities, transformation of the chirality of the fields. Okay, so you have to be exactly the same not to fulfill that rule. Okay, now you don't know who it can be, but it's obvious that there is only one candidate, because if I put a 2, 2 is 0. If I put a 3, 3 is 0. Okay, so only I equal 1 is possible in principle to write it. So, but now we see that 2, 1, 3, 1 has dimension of energy to 0. Okay, so cannot be. Okay, now my dimensionalities tell you this cannot be the case. Okay, there is no, I don't know how to say no. Okay, there is no possibility to have this thing. Okay, and now you start building up kind of selection rules of what is allowed and what is not allowed, depending on the helicity of the states. Okay, now you can derive all these things from the standard model. You tell your Lagrangian, you plug it. You have to know, it's in the notes, how to write your spinors as my spinors, the angle and the square is easy. Okay, it's also in the paper I put you at the beginning. Okay, in those papers explain how to do it, and you could do it exactly in the standard model from Lagrangian, coming back, and you would get exactly the same, of course. Here you get it in a faster way. The idea is to get it in a faster way, okay? But you get the same rules, okay? That only the Higgs can only coupled when the fermions, incoming fermions have equal helicity, okay? And we will see these rules are important, very, very important, okay? So now this is for the Yukawa interactions. Now the gauge interactions is the same, okay? The same rules to follow, okay? Now I have a boson A with helicity minus. When it's a boson, will be -1. I'll put it the first time, okay? Helicity -1, okay? But every time I put minus, you have a boson -1. A fermion is -0.5, okay? I already don't put it, okay? Oh, I can put it in this case, okay? Let's do it. Let me go for the minus and plus, okay? Because this, I'm going to show this is the one that is non-zero, okay? And now again, the rules tells me it should be proportional. Okay, again, 1, this is the particle 1. Because this is why I don't want to put the 1 and minus, too many numbers here, okay? Because this also I have to label the particles. This is particle 1, this is particle 2, and this is particle 3, okay? And now, okay, this is helicity -1. I know I should have 2 of them, of these guys, okay? Such that when I plug into the amplitude e to the I theta minus 2 times minus theta half, okay, will give me minus e to the I minus I theta, okay? Helicity of this guy is minus twice of the fermion, so I have to put twice here, and then will be proportional to the 3 also, and proportional to the 2 minus 1. Have to be always, as we said here, always, I go for this option, all of them, either bracket, either square, okay? But of course, I have to contract with something else, okay? So what contraction can be? Let me go here. Well, easy, I can contract 1 with 3, 1 with 3, but still remain the 1 to be contracted with somebody else, okay? Let me call it, again, I don't know who could be here. okay? And the 2 comes down here, but I have to contract it again with the same I, okay? So because without the I, this fulfills the right properties of the little group, okay? But if I put the same I, okay, this will not change anything. This will transform equally like this guy up and down, and the transformation under this little group will not change. The property will be fulfilled, okay? And now again, what could be I? You can see can be 1, 2, 3 in principle, but if it's 1, this is 0, if it's 2, it's 0, and now it's fixed, 1, 3, you see. Relatively easy, you start building up, it can only be 3, okay, so I write it like 1, 3 square divided by 2, 3. Second check, the dimensions, okay? This is dimension 2 divided by dimension 1, this is dimension 1. Okay, perfect, okay? This is our interaction. This is the amplitude that defines how a spin, a spin one object, okay? Massless spin one object, okay? So I have only 2 helicities, okay? Let me say now a parenthesis here that probably when I'm clear on all these things. I'm not using at all gauge invariance, okay? Because I start with the physical states, okay? Remember what is gauge invariance, okay? Is the pain we have to go when we go to fields, okay? So because fields, state, there is only the helicity, it tells you that there are 2 states, okay, of the photon, for example, okay, but we have to construct we want to construct our Lagrangian, we have to go to the same mu, have extra degrees of freedom, and now you have to put gauge invariance to kill them, okay? Now here I don't have a priori gauge invariance, okay, but, and that could be important to go faster, but you can ask the question is why I impose symmetries, because a priori, when you impose the gauge symmetries, you get the symmetries, okay? But symmetries will come here. I'll tell you how they come, okay? Okay, so this is it, and the last one that I left it for you, okay, is the gauge interactions. Okay, no gauge, three gauge interactions. 3 gauge bosons, let's say. Okay, and by the way, I didn't go through it, but again, this is something you can check. Can I have minus plus plus? Okay, and check it, you cannot have it. Okay, what you can have is completely equivalent one, like here. Okay, this same way we did here. There can be always the equivalent one when we flip all the helicities. Okay, it's just replacing angles bracket by square brackets, okay? You can change fully so I don't write it, there is one with plus here, plus and minus, where you replace this angle bracket by square brackets, okay? But there is no such that I have plus, minus here, for example, and plus, plus. Okay, minus, plus, plus, in the case of the gauge, doesn't give you anything. Okay, and equivalent here, I can only have 2, I cannot put the 3 plus, the helicity, I have to put minus, minus, a plus. And if you do it, you will get that this is proportional to 1, 3 cube to 1, 2, 3. Okay. It is already interesting to see that it's antisymmetric when you interchange 1, 3, 2, 3. Okay. So the coupling we put here, remember, this is the proportionality, what I'm getting. There is a coupling here, okay, because the amplitude, I don't know, up to some constant factor. The constant factor should know, okay, for example, I cannot have 3 photons. You know, doesn't exist in the standard model, 3 photons. Here you can see it because if it's the same particle, okay, this is odd and they interchange, okay, so it would be 0 if it's the same particle. So there should be a coupling here that has to be antisymmetric under the exchange of this. Okay, because it's also antisymmetric. So making antisymmetric will be symmetric as should be by the interchange of bosons, okay? So let me summarize here some sense I'll put it here, like the relevant couplings of the standard model, what we get, okay? We get, and now I'll put extra things. I'll put now also, if you have global symmetries, okay? If I have global symmetries, they should be multiplying by some invariant tensor with respect to the global symmetries you're imposing, okay? Now I'm going to assume I have these symmetries, okay? Because to prove how the symmetries are appearing is a very interesting exercise, and I'll show you a little bit how symmetries should be there, okay? Because I'm not coming from gauge invariance. I don't put anything extra a priori, and I would like not to put symmetries, okay? I don't like symmetries to put symmetry. Okay? I hate symmetries, okay? Sorry, but I'll have to put them, okay? At some point here, okay? Either one or the other, okay? So when I look here, I went for in this diagram, all others, all bracket, all square are 0. Okay, when I go to this one, all angles were 0. Okay? Either when I look at the coupling, either one or either the other.
So the second one can also be expressed as...
Yeah, there is equivalent here also. Okay, the Android, okay, you want me? There is the equivalent with plus minus, okay, that is exactly proportional to 1, 3 square, 2, 3. Okay, this guy can be, yeah. Either one, when I go for a interaction, for an amplitude, either for the full amplitude, either choose one or the other, okay? So for example, in the standard model, I can have a scalar Higgs. Okay, now I have flavors. Okay, I'm going to assume they have flavor. Okay, I'm writing fast the interactions that I can have. Okay, so I can have this interact with a fermion, has a flavor, so has an index. Okay, like SU2 index. Okay, and now this is a Yukawa coupling times, as you said, 3,2 delta, and now I have to put an invariant tensor, delta ij. Okay, I go for the vector interaction, has some flavor, so I put an A here, and the fermion has also some flavor. In the fundamental, vector are in the join, as in the standard model. So I'm putting the symmetry. Later on, I'll try to show that if I don't put the symmetry, I'm getting crazy things, okay? I will tell you what is crazy, okay? Okay, so this is already the one we discussed before with helicity minus and plus, okay? And this is equal constant. The constant, I call it G. Okay, this defines what is the gauge coupling. The invariant tensor of a joint and a fundamental is the generator TAIJ. Okay? Let's see if I can do it in the full thing here, in this piece of blackboard. I'll pack it a little bit. I go for so I'm building up from all these things now the standard model. The basic interaction, again, I have a vector in the joint interacting with a scalar that I have in the standard model with the Higgs, has flavor on the SU2. Okay. I put H dagger because, of course, both are incoming. Okay. Otherwise, and again, 1, 2, 3. And now helicity, this is minus. And now this is, here I could put another G prime. Okay, you could say, why you put G? Okay. You could put another G because nobody's telling that this G should be the same. The coupling of a vector to fermion should be the same, a coupling to vector to H. Okay, in the standard model, they tell you, okay, put gauge invariance, and now by gauge invariant. But here I could put it differently. Okay, if you want, you can put it differently, but we will see we are forced to have it the same. Okay, I don't know, I'll put it the same. Okay, but keep it in mind that I'm cheating here because I have not given to you the reason. Okay. This is this. I hope I don't make any mistake. Okay, it's the same as we derive it. The only thing I'm putting is the flavor. Okay, invariant tensor here, and the last one, completeness, VA, BC, again, plus minus, minus, plus. Okay, the ones I didn't put, I put only here, I said minus, minus, and plus. I cannot put plus, 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 okay? Try it. If you succeeded, you did something wrong. And now this should be some couplings. Okay, again, I put in the stem G, it should be different in principle. Okay, and this coupling should be antisymmetric, but I'm telling you we'll need the symmetry, okay? I'll tell you at some point that the symmetry is needed, so I already put in the Jacobi FABC, that is antisymmetric under ABC. Okay, and now this is antisymmetric, this is antisymmetric, this is symmetric, as it should be for an amplitude of bosons. Okay, now how to see that the couplings, what to do when we go beyond 3pt. Okay, this is amplitudes with 3. So the good thing, this is it, standard model is it, 3pt finished. Okay, 3-point functions, 3-point amplitudes are done. Okay, I think I don't leave any, 1, 3. Okay, I don't talk about gravitons, but we'll talk about later on a little bit, or I can put it as an exercise. Okay, because I want to go to higher point. Amplitudes. Now, we can do the following, we can say the same logic. But now we'll have to demand something, okay? Because now we are going to talk, for example, 2 to 2. And in 2 to 2, scattering 2 particles going to 2, now we have invariance, okay? Before we didn't have any Lorentz invariant of momentum, okay? But we know now we have 2 to 2, we have STU, the Mandelstam variables, okay? And now when we do our, of course, we have extra guys that we have to put in our amplitude. We don't know where to put it, up or down, okay? We'll see that it's easy to know where to put them. But now the dimensionality changed. For example, I couldn't do this because I didn't have the right dimensionality, okay? If I have some other invariant, like S, I could put it upstairs or downstairs to change the dimensionality. Because S and T and U, of course, and this thing doesn't change under this transformation, only the spinors, okay? P, if you want, look at here, is invariant, is the definition of the little group. The P's are invariant and products of P's are invariant. Okay, well, let's go for this. I would demand, because I have now STU, I will see that sometimes, in order to make it with the right dimension, I need to put STs and use in the denominators, and this will be singular when S goes to 0. I'll have poles, okay? So what I will demand with these poles, okay, factorization, okay, that is a property that you get in field theories, okay, it means that singularities, okay, this is a very important constraint, must be simple poles, okay, arising from particle exchange, okay, and on the pole, we go to the pole, you go 1 over S, when S goes to 0, and in this case, let's say the higher PT. Okay, let me take the example, the 4PT, because I will not go beyond that. I factorize in 3 PTs, okay? The 4, like amplitude, the 4PT amplitude should factorize in 3 PT. Okay, what it means, okay? And also for the rest, higher PT in the singularity should factorize in other amplitudes that you already have to have in your theory. Okay, if I look at for amplitude and I have a singularity, okay, 1 over S, okay, let's say it, when S goes to 0, okay, if I have a pole here, when I build it, I'll see that I need to put by dimensionality 1 over S. When S goes to 0, what I'm demanding is that this, okay, so it means that there is a pole, something over 1 over S, should factorize in 2 amplitudes, we call it left and right, that are 3 PT, okay? Should be a product 1 over S times an amplitude, on-shell amplitude, on-shell amplitude. One of those guys I have there, okay? More clear, put it here like much exact. Now I tell you with all the I's and all this. Okay, the limit when S goes to 0, if I have a singularity, I'm assuming that, of S times the amplitude of 4pt, okay, of a particle 1, when I have 3 particles, 3, 4, okay, should be equal to, and now there is some I's here that I put because of my conventions. Some other conventions, and if you look at other reviews, you will not see it, okay? Let me write it, and after that explain things. Thing is clear from what I write. Yeah, these extra factors I's is just conventions. Okay, the key point is that this amplitude S times the amplitude when it goes to 0 is a product of 2 on-shell amplitudes. Okay, you know it happens when you do, no? When you calculate the Feynman rules and okay, and you have a production of a particle, you can produce the particle, you can get into the, you can get on-shell, and is the product of the 2 on-shell amplitudes, okay? Here. So this is the condition. There is a subtlety. I'll come now again to tell you, but sorry, tell me first question. This I'm assuming 3 level, okay, and all my states, okay, massless, okay, are stable. Okay, yeah, when we go to loops, another story. 3 level, but this, look, this is what you do also when you do quantum field theory. You start building the Lagrangian and you never, okay, no? You write your operators, and you never ask, you have a G there, and you never say, this G is running, is what the G is running G, what is this? No, okay? So formally you can take it. For me, it's very clear when you think, okay, this G goes to 0. Okay, so quantum roots are 0 completely. Okay, this is a formal limit. It's good to think about formal limits. Okay, okay. Something is 0 and loops. Good. I define my theory in this limit, and after that, G is going to be constant. And now the particle can get width. Okay, masses. I'm taking massless particles all the time. Okay. Is it?
Always possible to factorize.
It should be always possible. This is the point. You should demand this thing. You should demand that use massless pi. Yeah. This should be a property that you have, and you have it when you do quantum field theory. I could argue about these things, the way the singularity is like this, blah, blah, from other arguments, but I don't want to go through it. Okay, you just can think, okay, I know when we do quantum field theory, this property exists. Okay, I can factorize always the amplitude. Okay, so I'm using now that your knowledge of effective field theories, okay, but tell you that this should be required. Okay. I'll put an example and I'll show you, but yeah, because I didn't define F. F is the F is equal to 1 if there is a if the internal, if it is a fermion line. Okay, if it is, this is a fermion. Okay, let me. Okay, if the exchange particle is a fermion. I will not put much emphasis in the I's, okay, but okay, this is exactly when you want to calculate it, you have to be precise with the signs, I's, and all these things. And why I wrote it like this, because there is a subtlety, is that the momentum goes in one direction where you have this, no? Either goes like this, okay? So, but I was talking always about amplitudes incoming, so I have to face a problem. One can be all incoming, one has incoming, one outgoing. Okay, this is the P momentum going in that direction. Okay, so I have to flip my spinor, okay, for minus P changing and this is a convention, changing the sign of the P, okay, and to make it, because I like to write I wrote all of them with incoming, okay, so some P might change and I have a conventions, okay. I will not be very strong because convention is when you, I mean, all these things is when you need to do exact calculation and get the precise things, okay. That when the spinor has minus P, okay, I write it like this, it can be shown, okay, convention, I can do that both either angle or square spinors and get an I. There are different conventions. Some people say that the angles don't change and the P change. What is important, so the important thing is to fulfill okay, that of course if I have minus P, okay, if I write the minus P, the product, okay, this is the momentum, okay, has to be minus PP, okay, so this is a minus P alpha dot we were talking, okay. Should be a change of sign, of course, in the momentum, okay? Of course, if you change the momentum, I have to be a change of sign. So the product is fixed to be, okay? The product of this thing should be minus this, okay? This is what you need. This is the real property, and now I split it half-half. E, I, and I go each, okay? But some people say that this doesn't change sign and the other change sign. And important property is this one, the change of sign, okay? Let me go for the exercise. If, or let me take questions. Tell me if, zeros, yes. Otherwise, okay. Boson 0, yes. Yeah, these are conventions. You have to spend a little bit of time to get the right eyes and everybody. Okay, you will see reviews different. This not would be the, it's important you ask, okay, but this is the key, this is a key, very important property, okay? This is extra, you demand now, because we're going to go to physical amplitudes, okay? And we go to physical amplitude, we demand this, okay? There will be singularities, okay? And when I go S0 or T0, I want this to be, there is a particle there, okay? And factorize in something I already have. And this is the way I build up. These are the building blocks, and I can build up higher PTs from these things, okay? This is what defines the standard model. It's still missing one coupling more here. You didn't ask. We're still missing a coupling in the standard model, but that is a 4PT, a 4-point amplitude, okay? But try to get these things, okay, at some point. Sit down and try to see if you can get these things. For example, the plus is 0. Try to do it, okay, following these rules. Okay, it's just in few seconds you realize that you cannot make it. Okay, this has to have dimension 1. Okay, and transform properly and have this property. Then knowing that this is -1, or you could take plus 1, plus 1, plus 1. Helicity of the 3-gauge boson. The nice thing is this, that the building up of the standard model, okay, it looks like as a function of these factors, okay, but of course we're able to define these 3-point amplitudes because of the complex momenta, okay. Let's try to do, have little time, okay, we have to do, let's try to do an example. More difficult example, I leave to you the example of gravity. It is easier. You see, the higher the spin, the easier it is, okay? Okay. And this is the amplitude of the standard model of Let's put a little bit of everything. We have a scalar, we have a gauge boson, and two fermions. Okay? Label the particles, 1, 2, 3, 4, all of them are incoming, and now I choose the helicities, minus, minus, plus. The total helicity, okay, is +1 from the vector. I put a plus, but it's +1. It's a fermion minus a half minus a half. 0. Don't have to be 0, it's any number, okay? The others are non-zero. This is -1, this is +1, the total, the sum of helicity of each particle. This is minus 1, and go on. Okay, don't have to be 0, but we're looking to 0, and we will see that 99 or 90% of the standard model are all 0. The surprising fact, okay? So the first thing I do is the same thing. This is scalar. I don't have to put helicity. I think it's everything. Okay, because I do the standard model, probably I have to put flavors. So I have I have a Higgs dagger coming in. Let me put the flavor, just if you want to know. And there is a line coming, and there is the fermion J, and the fermion that is not carried in. So the flavor goes in one direction, okay? Now the question, what could be this amplitude? Some constant, I don't know. And now I want to fix, in the denominator, I'm going to fix the transformer properly under this, okay? The Higgs helicity 0, so should not be more angles than, it should be the same number of angles than the square of the 4, okay? But the 3 again, okay, let me start with the 1, 2. 1, 2, I can put them like this, and they have the properties of this is spinor, because spinors are easy. These are fermions. I have to have it's minus minus. I have to have angle and angle for these two guys, and I contracted among themselves. And now this guy is a plus, so I have to have a square 3. I cannot contract it with the other 3. Okay, that would be perfect for the helicity. We'll have 2 3s, will give me, under this property, will give me the right thing. 2 times e to the theta half would be theta half, the helicity of this guy. Sum the helicity of the spinors will give me the helicity 1, because this is 0, okay? So again, I have to put a guy here. I don't know what, I'll call it I, because I don't know who could be. And I have 3, and I call it J. Okay, because I don't know who could be here, but because I'm putting I and J, and I don't want to change the helicity properties, okay, I have to put I and J. So wherever I put I and J, they have the same number of square and angles, so will not be any phase associated to them. Okay, sorry, put it in red. Let's put it in red. Okay, this is the denominator fulfilling the properties of the little group and the helicities of the particle here. Okay, let's go for the denominator because it has to be dimensionless. This is at 4 pt amplitude, dimensionless. Okay, let's count dimension 1, 2, 3, 4. It should be here. And now I have extra guys for doing it. Okay, because this is a 2 to 2, I have the S, T, and U. Variables, okay, kinematic variables, Lorentz invariant variables, okay? And I can put here, I could put S squared, but now I say no. All the poles and simple poles, so I can put one S. I have to put another guy, T or U, okay? Let me put T, because I can feel that the charge, okay, here, okay, this is telling me that there should be some diagram that looks like when S goes to 0, it will be associated with a pole in the S channel, and when T goes to 0, this will be associated to the pole in the T channel. Okay, and because flavor goes in that direction, I chose the fermion to be charged, this guy. Okay, this diagram exists. Okay, where flavor goes like this. okay? And because it has flavor, couples to this W, okay? But this is come later, okay? This I'm saying here I would have the freedom to choose if you want U. You have 3 guys, okay? So there is some choice to put, but this will be associated with different theories. I know if I want to get to the 3 point, okay, you could try the other possibilities as a U, and now will not factorize with your standard model. Let's define it like this, okay? Because you will have poles. So I advance a little bit that these poles give you the right properties, okay? But, so we learned something that we require by on-dimensional grounds to have 2 poles in S, or either T or either U, okay? Now we need factorization, okay? Let's impose factorization, okay? Okay, we take S going to 0, and now we say this, okay, in this limit, this amplitude, okay, there is a singularity S and singularity T. Okay, let's take the one in S, should factorize, of course. Okay, so it should be Higgs. Factorize means that there should be, if he didn't want to put it, you see now, this amplitude is telling me, if I write it like this, there should be a particle exchanging in the S channel, okay? So if I forgot the standard model, there were no coupling in the standard model in this theory. I didn't put it, now we'll see by consistency I have to put it, okay? Because when I write this amplitude, the amplitudes exist, or either it doesn't exist, but if it exists, I have to put it. Because when S goes to 0, you have to factorize. So there will be some body exchanging here. It can only be a scalar, okay? Looks like a Feynman diagram, but it's not. It's just taking factorization. I'm saying I have the product of this and the product of this, okay, when S goes to 0. Okay, sorry, I didn't write it correctly. Factorizing this guy here, vector and 2 fermions here. And now factorization means that, and factorization will tell me also who are these IJs and tell me will be these things. Okay, factorization will fix me the information I didn't know here. Okay. So let's see if it goes in the right way. Okay, so we're going to take the diagrams by knowing that this vertex, okay, is this one. I'm going to put, okay, where it is this one, and the other vertex is sorry, one vertex is this one, and the other vertex is this one. Okay, so I take this thing, that thing, okay, that thing should factorize to this product. Okay, so I put the product here, which should be by reading there, okay, to see. Okay, if it's consistent, this should be exactly, and this is the Yukawa coupling times 1, 2. Okay, there is 1 over S, pole. There is 2 i's there, but doesn't matter, I square. And now there is this guy here. Okay, and I'm going to call this particle P. Okay, the same, I call the particle with the momentum P. Okay, the same, the momentum that it carries, okay? So reading the 3pt from there, okay, this should be 3, 4, 3p. You check it that this is exactly P4 for these 3 particles. Okay, times G times TA J. And here I have a delta Ij. Okay, in the middle, this is 1 over S. And now I'll do a little bit of manipulations, okay, to get it. Okay, and this is exactly, you see the coefficient that comes in front is going to be G, the Yukawa coupling, you see, this is going to tell me who is this guy. It cannot be anything, it's not free. You're not free to choose what you like here. A priori, yes, but after that, your vectorization fix it to be Tij, 1, 2, There is the minus signs for from the i's. 1 over s, 3, 4, 3p, p4. And now I start a little bit of tricks to write it in a simpler way, this thing. So see, I want this to look like, at the end, something I have here. Okay, this is what demands factorization, okay? And this will fix me what are these ij's and what is this constant, okay? So I have to do little tricks that when you get used to it, you see it automatically. Multiply here by P2 upstairs, P2 downstairs. And now I see that this is P. Okay, P is always the product of these spinors. And P, okay, see here is exactly the momentum coming in is exactly minus the momentum of the particle we call 3 and 4. Okay, so this is minus P3 plus minus this and P4. So where you see P, I can put 3 or I can put in 4. But if when I put 3, this is 0, because 3, 3, and only the 4 will remain, okay? Similar here. Okay, so at the end of the day, this can be written as, this factor. Okay, this can be written as a minus G. Okay, I'm not doing bad. This is this factor 1, 2. And now I have, if you don't see this, I can tell you later on how to do it. Okay, I will have it's the conservation of momentum, the property I told you, but is, so it will be 3, 4, and the other will be 4, 2. And down there, the 4 cancel because it cannot be, it has to be 3. There's a minus, but the minus upstairs and minus downstairs, I don't put it. And 3, 2. Getting closer to something looks like here. Okay. Going slowly, but usually this can be done faster. But in order to get even closer to the thing, upstairs, I don't know if I made 3, 4. I can kill 1, 3, 4. Yes. Okay. I make it closer to the thing. I multiply here by 2, 3 upstairs and downstairs. Okay, I'm doing. Okay. I want to get it approaching what I have there. And S, what is S? S, I can write it as I have a T here, so I can write S and T, right? S is 2 times, okay, P1, P2, okay, massless particles, so S is 2 times P1, P2. That can be written, or also P3, P4, okay, conservation of momentum. So I can write it like 4, 3, 4 in spinors, and T, I can write it like 3, 2, 2, 3. Now probably I skip it, otherwise it would be too much in detail, okay, but so I have S, sorry, but this I need it, no, I need it later, S. I just needed to have T to get a T down there. Okay, this is why I multiply by this, okay, because this will give me exactly T or minus T2, 3, 3, 2, exactly exactly T, yeah. Okay. So, and of the thing, I'll have ST minus, I'll have upstairs 1, 2, 3, 4, 3, 4, 3, 2, 4, 2. Okay. If I didn't forgot anybody. Okay. So factorization tells me this should be equal to this. Okay. Okay, so equating this that come from when s goes to 0, this should be the product of these two guys that I already have. Okay, fix me the C to be exactly G eta minus that, okay. Okay, see the minus come from 2, 3, has to go to 3, 2. Okay, to write it as I have it there. Okay, that's, so I was missing this minus sign here, and now, yes, this guy is G times hypercharge TA ij. This is the coefficient. C and the I and J are fixed. Okay, the I is 4 and the J is 2. Okay, so I can be a healthy amplitude. Okay, can be a good amplitude, this one that we build by conditions. It could be that it's not healthy. Okay, for example, this is not healthy. Of course, no, on dimensional grounds on double pole. Okay, this seems to be a priori a healthy amplitude by looking at the factorization at the S channel. Okay, if C is fixed to be this and IJ are fixed to be this. Okay. What was the? Okay, C. Okay, well, C was that thing. Okay. Now you have a second condition. Okay, because by constructing it, okay, to have dimension 0, we put a T. Now T goes to 0 and you have a singularity. Okay, so second part, you have to show that, I leave it for you, that there is a T channel, okay, that this guy, it is in the standard model, in principle, so good. If it's not there, I should put it. Factorize into amplitude, this one in the T channel, and fermion going to both, okay, this one. These 2, 3 PTs. This one and this one. Okay, this is now an extra condition. Okay, and now comes the point I was telling you. Imagine you didn't want to put symmetries, or imagine I wanted to put different G's here. Okay, why not? I don't have any argument. They are proportionally. Okay, now you will see that if you go for factorization, okay, it will not factorize. You put a different G. Okay, remember that we already, for the first factorization, we already fixed the C to be the Yukawa couplings times TA IJ. Okay? If you put another G here, G prime, you're not going to get factorization properly. Okay? So when T goes to 0, I find another singular thing. So you see, it's completely different as it comes from Feynman. Feynman, diagrams, you have your theory and you start building, okay, there is a T, there is all the Feynman diagrams. Here in some sense, it's forced upon us. It's forced to have these two. It's the only way I could build this thing with the right dimensions. So I got 2 poles. okay? And now I have to satisfy this thing, factorization, okay? In the S channel, fix me one, the coupling once, but now I really fully constrain. I have this thing, or it works or it doesn't work. And it works if you want to change the G's, it will not work, okay? So the G's should be the same, okay? So the G's are not fixed by gauge invariance, okay? They're fixed by here, by demanding that all singularities, all the poles, okay, are simple poles and factorized in 3-point amplitude that you have already in your theory, okay? It's completely different concept that comes here, the thing. And the same with symmetries, okay? Similar thing with symmetries. If I don't want to put a global symmetries, okay, this is a little bit longer exercise. If I don't want to put global symmetries, okay, you will see factorization does not work, okay? If I had interchange, I would not do it because it will tell me, very good, okay? Let's say you put U because I had the freedom, okay? Went here a little bit not to be, okay? If I put it, U will mean that I have a singularity U, okay? When U goes to 0, I have to factorize, okay? So I have to factorize in the U channel, okay? Now I will have, okay, let's do it here, have U goes to 0, and now I have to factorizing in the U channel, okay? So I'll have this factorization, okay? It's always difficult to draw the U channel. In this channel. I have to factorize on this. But when I chose my quantum numbers, I didn't put flavor here, okay? Okay, so I don't have, this is a singlet. How come a singlet coupled to something that is not, that has WA, okay? In the moment I decided this fermion was the one that carries the flavor index, okay, I already fixed the T. I don't have this thing in the standard model, okay? So all the possibilities are, all the ways that you can think are closed by the factorization thing. 3. Putting something here. Yeah. You could test, but this, okay, the way I proceed, I first fix upstairs. Yeah, you can multiply, you have to, yeah, you can do it in different ways if you want. Okay, but the way step forward, I fix the elicities, okay, the little group transformation by denominator, and after that now I have to fill with this invariant thing, okay. You will do it, please, you will get the same, okay. Do it, yes. In fact, this amplitude, if you spend some time, okay, time is over, I'll give it to you, can be packed in a beautiful way, okay. Remember, I wrote you here, now it's not anymore there, what it was S and T, okay, as a function of brackets, okay, and it's a beautiful, simple thing. Okay, you would not foresee such a simplicity. Well, this was from the Feynman point of view, okay? You can write it like this. Okay. Now do it a la Feynman, okay? You have an extension and try to prove that the n, okay? Okay, you can write it like this. Okay, here is straightforward. Okay, you only replace S and T by the spinors I had here. Okay. Yeah, over. Okay. So try to do at least some of this amplitude if you're interested. Okay, because it's relatively easy. Okay, so when you put into the game. Okay, and we'll try to do this one. Graviton now. I think you are prepared to do it. Okay, graviton plus, minus. Okay, it's +2, it's a graviton, +2, -2. I think you can do it. Okay, okay, there is a G Newton times, fill the numerator to fulfill the elicity, the little group transformation in the numerator, and now fill the denominator with ST and U's. Not double pole, only one ST and U. Next day I put it, okay. Try to do it, I think you can do it, okay. I think you can do it. And that's it. Okay, I will show you. Tell me how long it took you, okay? But I always say you can do it in the 10 seconds, but of course, when you are used to go faster to build up the numerator, okay? I demand this, I demand to amplitude to be healthy, okay, I demand, okay? In some sense, I can demand, the best way I tell you, because I don't want to get into other argument, is that when you do tree-level, in your quantum field theory, you do tree-level, okay? You have factorization, okay? So it is also, can be defined in different ways, okay? But at least, okay, this is the simple. I have factorization, okay? So this is the only thing I use, okay? That should be this problem, okay? I have to factorize in 3pt, so. Exactly, this is a fictitious thing. This is a fictitious thing, you don't have. Try to do it. Try to write it, okay? Yeah, I didn't say anything here. Okay, next day, but otherwise but try to write it again. Yes, 4, you say 4pt has to be dimensionless, is a 4 thing, and now try to put plus and minus here. Okay, try to do it. No, it's a fictitious artifact of the, demanding gauge invariant. In fact, if you go to, when you look at the amplitude, okay, that contact term only is to make it gauge invariant. There is not really, there's always singularities there. There is not a contact term. Never a contact term there. Disappear. The contact term, no. So these are things that you had to play with when you do the gauge invariant, okay, all these efforts. But here, if you went over the thing, understood this thing, now you can build, everything is easier.